In this video, we're going to look at the volumes of solids of revolution. And what that means is we're going to take a curve, rotate it around an axis so that a solid is formed, and we want to calculate the volume of that solid using the area of the base times the height type arrangement. So let's, but before we begin, let's just start with something simple here. I'm going to, just to set the scene a bit, let's say we have some curve like, we're going to set up a set of axes like this, and I'm just interested in the point, say here. I'm just going to pick a point whose value is r. Okay, the point whose value is r, and I want to take this point now and I want to rotate it around the x-axis, so that what I end up with, if I were to look at it a bit like this, is I'll end up with, if I rotate it at r here, I'll end up with a sort of circle. So what I'll have is a circle, infinitely thin. Okay, the circle there. Okay, if I rotate it about the x-axis, and at the value of r, y equals r, and the area of that circle formed, the area here, will be, the area of that circle will be pi r squared. It's a circle. This r is just a constant here, it's just some number on the y-axis here. Area will be pi r squared. Now, what if I draw that curve out a bit and out some distance dx along the x-axis? So what I've now got is my curve. It's going along f of x, y equals f of x is equal to r. Okay, now what I'm going to form when I rotate that about the axis is I'll form a thin disk, a disk of thickness dx. Okay, now the volume of that disk, the volume, actually, let me write volume. The volume, okay, will be the area of the base, pi r squared, times the height, dx. So that'll be my volume. Okay, now let's say I want to run that dx between, follow this curve along, and let's just say I might want to run it from x equals 0 to x equals some value, or I might be interested in, say, running it from x equals a to x equals b. Okay, so what I then have to do is I've got an infinite number here of little thin dx's, infinitesimally thin, infinitesimally small dx's. And what I want to do is I can sum all those up. And so the volume now becomes, when I sum all those little infinite number of little dx's, infinitesimally little thin slices dx, the volume becomes now the integral from a to b, pi r squared is, remember, r squared is just f of x squared, okay, y, okay, f of x squared dx. That's my volume. All right. Remember my little thin disk at the beginning here, infinitely thin disk. It was just a disk with no thickness whatsoever. That area in here, all this, was pi times r squared, or just pi times f of x squared. Okay. Now, I then introduce a little amount dx here, a little dx here, and the volume of that little first little disk here of thickness dx, so it's a thickness or height dx if you like. Okay, the volume is m pi r squared times dx. If I now sum all those little dx's between a and b, then that is the integral from a to b of pi times f of x squared dx. Okay, and that gives me the volume of revolution. That gives me the volume of this solid in here. I could set a equal to 0, for instance, and then I've got the whole lot from 0 to b, from x equals 0 to x equals b. That is the idea. That's what we're going to do today. That's what this video is about. Okay. So let's have a look. Now, instead of just that straight line, what we're going to do is, let's say we have some curve. Here it is, y equals f of x. Okay, y equals f of x, our curve. Okay, we're going to rotate this about the x-axis, all right, between x equals 0 and x equals b. We'll just call this x equals 0 a, because it doesn't have to be at x equals 0. It could be, say, it could be, for instance, from here, a. Okay, then the volume of that region there, that solid that's formed, will be the integral from x equals a to x equals b of pi times f of x squared integrated with respect to x. Okay, x going from a to b. We could rotate around the y-axis. We'll take our curve y equals f of x and rotate it about the y-axis. Okay, in which case the volume will be the integral y equals a could be 0, could be anything, y equals a to b, pi times f of y squared integrated with respect to y. We could take this a little bit further. Let's say we have two curves. Okay, we have f of x on the top here, g of x underneath. We're interested in the region between x equals a, x equals b, and we want to rotate that about the x-axis. We're going to form a donut-like shape. Okay, we're going to form a donut type shape, a wheel type shape, a tire type shape with this region all in here will be empty. Okay, then the volume from that becomes pi times integral a to b f of x squared, the top curve, minus g of x squared. Okay, integrated all with respect to x. Okay, that's the volume that's formed. Area of the base times the height, whereas the height goes this way, or in this case, in the y case, it goes up. But either way, you have pi times the radius squared, and then integrated time in the direction x or in the direction y to give you the height. So pi r squared times height. Okay, just as we think of the volume of a solid, such as a cylinder. All right, let's have a look now at some examples. Let's take the first one. Here we got y2 on top, y1 underneath. y2 f of x is cos x, and x is between 0 and pi on 2. Here y1 is g of x underneath, which is a square root of 1 minus x squared. X is between 0 and 1. All right. And we're going to rotate that about the x-axis. Okay. What's the volume of the region formed? So the volume will be pi times the integral f of x squared dx between 0 and pi on 2. Okay, minus the integral of minus pi times the integral 0 to 1 g of x squared dx. Okay, so we're taking y of 2 revolving it around the axis to give the whole volume, and then we're going to subtract the volume inside covered by y1. Okay, to produce the volume of the odd sort of bowl-like shape, bowl turned on its side, like a little, I don't know, a dish type arrangement because it comes down underneath. All right, so when we do that, pi times the integral 0 to pi on 2 cos squared x dx minus pi times the integral of square root of 1 minus x squared all squared dx. That gives us, using trig identities, pi times the integral 0 to pi on 2, a half times 1 plus cos 2x dx from the integral identities, trigonometric identities, minus pi times this object here, 1 minus x squared. Okay, we got rid of the square root sign because we squared it. Okay, antiderivative of a half is x on 2, but we'll take that pi on 2 outside, we'll factor that out. So antiderivative of 1 is x, antiderivative of cos 2x is sine 2x on 2, okay, integrated, and the terminals are 0 to pi on 2. On this side here, antiderivative of 1 is x, antiderivative of minus x squared is minus x cubed on 3. Again, the terminals 0 to 1. Let's evaluate the terminals, 0 to pi on 2. Well, pi on 2, and here sine of pi is 0, minus 0 plus 0. All right, over here we have 1 minus 1/3 and minus 0, 0. And when we do that, we get here pi on 2 times pi on 2 is pi squared on 4. Here we get minus pi minus 1/3 pi. Minus pi plus 1/3 pi. So we get minus 2/3 pi. When we work that out, let's factor that out. We have pi on 4 minus 2/3. Approximate numerically to 3 decimal places, you have 0.373 units cubed. Remember, units cubed volume. Let's have a look at another example now. Let's say a sink is formed by the rotation of the curve 8y equals x cubed. Okay, y is greater than 0 about the y-axis. Okay, if the if the depth of the sink is 8 centimeters, okay, how many cubic centimeters of water could it hold? So if the depth is going to be 8 centimeters, okay, we're going to rotate about the y-axis. Okay, all right, now let's start from, so here's the plot. Okay, okay, and we want a depth up to here. What sort of volume could that hold? Rotate that about the y-axis, and what sort of volume? Now, from 8y equals x cubed, we can write y equals 1/8, times x cubed. But we want rotation about the y-axis, so we need a function of y because we're going to rotate, we're going to integrate dy in this direction. Okay, we're going to rotate about here and integrate in that direction. So therefore we need a function of y, so we want x equals f of y. All right, now y equals 1/8 times x cubed, so 8y is x cubed, cube root both sides, 8y to the third, x to the power of 3 to the 1/3 gives us 2y to the third equals x. Okay, and then the volume will be pi times the integral a to b x squared dy. We're going to integrate in the dy direction, okay, between the curve and the y-axis. So that's pi times the integral a to b f of y squared dy. X equals fy is 2y to the third. Okay, we want a depth of 8 centimeters, hence y equals 8. So there's our upper limit. Also, f of y squared is 2y to the third squared is 4y to the power of 2/3. So v equals pi times the integral 0 to 8 f of y squared dy is pi times the integral 0 to 8 4y to the power of 2/3 integrated with respect to y. Take 4 outside. 4 pi integral 0 to 8 y to the power of 2/3 dy. Okay, so that's going to be raising that by 1. That will give us 5 pi on 3 divided by 5 pi on 3, which gives us the reciprocal 3 on 5, evaluated between y equals 0 and y equals 8. When we do that, we have 4 pi times this object here. This is 0, and that gives us 4 pi 3/5, that to the power of 5/3. 4 pi 3/5, my apologies, 3/5 to the power of 5, okay, 32. Okay, so that will equal 12 pi on 5 times 32, and altogether multiplying that out, that'll give us the volume is 384 pi on 5 cubic centimeters of water, given that we're working in centimeters. All right.